Yeah, what I was saying was that this is finally we have come at the still someone entering. We have come to the not last assignment. Let me clarify. This is the last PLC programming assignment. What's been left out till date is a little information about PLC hardware, which is extremely important if anyone wants to appear for a core sector campus interview. Because there, of course, programming is important, only the basics of it. What's far more important is PLC hardware configuration and all that. So probably a little discussions on that. But when it comes to programming of PLCs or assignments on PLC programming, this would be the last assignment. And as you know, that breakup of labs is evaluation is 20% attendance, 50% class performance. And class performance is whatever you're doing. This assignments that you show is class performance. And rest 30% is supposed to be some same end evaluation. So what we are planning is, though not 100% decided, but what you're planning is you need to support 2 or 3 or 4 reports probably. So that would this one be against that last 30%. So of those reports, one would be on that 4 to 20 milliampere transmitter or a V2I converter that was done a few weeks ago. One report on that. Probably 1 or 2 reports on PLC hardware. So probably that would be it for the last 30% marks. Anyway, coming to today's topic. Well, this is the last assignment, PLC programming assignment. So needless to say, this is also the most difficult assignment that we have discussed till this point. The inputs that I haven't still provided is the previous assignment on that on-off controller, level controller that BD had discussed probably last week or the week before that. There, of course, one part is the on-off controller. The second part would be you need a process to ultimately try out your on-off controller. I just posted that part yesterday, and rather today, early morning. And the third part would be an HMI, which I just gave a demonstration, quick demonstration last week, which would contain a graphical display of the tank with water filling in or emptying. Second is you'll have a bar graph, not a bar graph, sorry. You'll have a trend chart recording. And thirdly, you would have alarms using the built-in feature within the courses. And fourth, another feature has been added. Of course, I'll thank Sangeet Sarang of your class. He found it out. I couldn't get. He found the solution of how to make that work. Courses are a matter of fact, all similar, this one, competing softwares. They provide a feature which is called remote monitoring, something that is very useful these days. What that means is every PLC, every decent PLC made by any renowned company, it features what is called a web server that is built into the PLC software. Now, if you connect this particular PLC, we have seen what HMIs are or what visualization is. Visualization is a term that is used in courses, but the normal name that is used for this is visualization. So you're seeing various variables, you're seeing graphics, you're interacting with inputs, viewing outputs using a computer screen, but then that is local to the machine, right? You have a machine that is hooked up to a PLC. In this case, we don't have a PLC. We are using a simulation mode. But even if you have a normal PLC, what happens is you have a PC that is connected to the PLC using an Ethernet connection. And this entire HMI or the visualization is seen on this local PC. Local PC means it's local to the same plant. It's located in the same plant or same factory where your PLC exists. It's just a visualization window. It gives you a view of whatever is happening in this entire factory or entire process, all kinds of inputs, all kinds of outputs, and all kind of information is displayed graphically and whatever mode. You know what visualization is all about. Now, an important feature is if you connect your PLC to the internet, of course, you all very well know about IoT, or that extended to an industrial environment becomes double IoT, industrial Internet of Things. Now, that very concept, that is, if you connect your PLC to the internet, then what could happen is you could have this visualization being displayed not on a local machine. I mean, local machine means you don't have the machine that is located within the same plant. It could be any remote machine that is connected to the internet. What it means is you have a PLC that is connected to the internet. Say it's located at your house, and you have another computer that could be located anywhere within this particular globe. The only requirement is your PLC and that particular computer both connect to the internet. In that case, what could happen is in that particular remote computer, you could have this entire visualization. That is, whatever HMI you have or whatever visualization that you have, what you have developed so far, now that visualization, instead of being displayed on a local machine, I repeat, local means it's a machine that is located within the same factory, same process plant or whatever. It could be located anywhere in the globe. So you connect that particular remote computer to your PLC. Your PLC has got a software, it's called a web server. What it does, it takes all the important parameters available within this particular PLC and transmits that to the remote monitoring station or display station, and you can have the entire HMI, you can have the entire visualization being displayed at a remote point. Now, this is now widely used for maintenance purposes. It's not used for regular, this one monitoring of a plant or regular control of a plant. I'll come to the reason why. But this is a feature that is now widely used for maintenance from a remote point. So you've got a system, you've got your this one, a process plant, you've got your equipment, you've got your machines. Something has gone wrong. So what are the normal practices? You call up this vendor. Vendor means the person who supplied these machines, the automation system. You call him up. He comes over, and then tries to troubleshoot what is wrong with the system. Now that particular vendor does not come to your plant. He simply, what he does is connects that particular PLC or the automation system over the internet to his remote office, and from the remote point, he monitors the entire system and then troubleshoots it, if necessary, corrects any malfunction within the system. Of course, you can't make a hardware change, but any troubleshooting, any debugging can be done from a remote point, because now you're connecting your PLC or your automation system or your control system to the internet, and you're monitoring the performance of that particular system from the remote point. Now that feature is built into courses as well. It is called WebVisual, WB Web and Visualization. They've taken the Visu part. Whenever you open a project, that WebVisual part is automatically added to your project. Probably you haven't noted it because you never used it. How to use it is very simple. So I'll send you a write-up of, I'll just send you a courses help page which says how to use it. It's extremely simple. But in this case, we are not using a remote machine. What we'll be doing is we'll be seeing this visualization on the web browser. Okay, what I missed out is when you're monitoring the performance of your automation system from a remote machine, you don't need to install courses in that particular remote machine. All you need is a web browser, and the web browser now provides you with the visualization display, which provides you with the HMI display. Whatever you see within that visualization screen of courses would become visible within a web browser of the remote machine. So all you need is a standard web browser on the remote machine. You need to connect to this particular PLC at a remote location, and then that remote machine provides a display of whatever happening in this particular machine. But the only downside to this particular approach, as you've guessed it, is very serious security concerns. No one normally wants to put up his machine, an automation system, a PLC, or the control network. No one really wants to connect that to the internet. The reasons is obvious. If anyone gains unauthorized access to your control system, then of course anything could happen to your control system, anything could happen to the operations of your plant, anything could happen to the operations of your factory. So it's primarily because of that particular reason that no one really wants to connect his automation system or his control network to the internet. So normally it is not connected to the internet primarily because of security concerns. Only when you're trying to perform remote maintenance, this becomes a standard feature. Then of course you connect it to the internet, you take necessary safety precautions, you use a VPN, you use a very strict password registration and all that security measures are there so that no one can have an unauthorized access into your system. But the whole idea is we will be seeing how to display the HMI, how to display the visualization on a remote machine or on a browser within the same machine. Of course, we don't have a remote machine. In our case, what we will be doing is we will be using the web browser. We'll be using the web browser within the same machine, which contains courses to display the visualization, to display the HMI. Know that this is not a restriction. We're doing this just because we have got one machine. If you connect your a machine to the internet, then of course you could see this visualization on any web browser on any remote machine. So that is the part that is also included. What we'll do is we'll see the visualization of that particular tank on a web browser. So that completes the previous assignment. I'll send a write-up on that visualization part. I haven't sent that as yet. And the last assignment, of course, I'm not talking about the logic. I'm just talking about the requirement. You know the system very well. You've already guessed it. We are talking about an elevator or lift, whatever you call it. So we are trying, this is probably the first assignment for which you really need a PLC. All the assignments that we have done so far doesn't really require a PLC given the kind of logic that we have used. For such small logic, no one really would use a PLC. It is economically not justifiable. But this one, well, this probably is one of the applications which really needs a PLC. Now, we would like to make it as simple as possible. So we are limiting the number of floors to ground plus 3. That is, we have ground plus floor 1, floor 2, floor 3. You can increase the floors, only that the logic becomes bigger, not more complex. The same logic extends and becomes bigger. So no point doing that. We'll limit ourselves to just ground plus 3 floors. Now you have this rectangle. It's a very crude representation of my lift. And this, what it looks like a diving board, is actually each of the floors that I've tried to represent. I just trying to jot down, or just trying to note down what should be the logic like. Okay, now how you go into the implementation of it, I'll come to that a little later. So the crudest of things, ground floor is floor 1 to up to floor 4, and this is a lift which could move from floor 1 to floor 4. Right? I've also sent in this one write up on this one, the control of elevators. I just sent it a little 1 or 2 hours ago. Pretty good write up. I'm saying all the things in short. You could have a look at that. Actually, the requirement is, you know what the requirements are of an elevator, but still I'm just repeating it. There are 2 sets of controls. One is on every floor, you have this particular control which is shown on the right. You have an up arrow button, you have a down arrow button. Of course, this is on the floor 2 and floor 3. When you're on the topmost floor, you cannot go any further up. So you have just the down button. And when you're on the ground floor, you cannot go any further down, so you just have the up button. But on second floor and the third floor, rather on floor number 2 and floor number 3, you have both these buttons. This up button indicates that you want to go up, and the down button indicates that you want to go down. This arrow, which is another display, which indicates the present status of the lift, whether the lift is presently going up or the lift is presently going down, or if it's off, it means the lift is stationary somewhere. What is not displayed is normally at this particular point, you also have an indication of the floor. Where is the lift currently present? That's not given in this particular display, but normally what is also displayed is the current location of the lift whether it's moving up, whether it's moving down, and those two buttons by which you can indicate that whether you want to move up or you want to move down, right? That is there on each floor. And inside the lift, what you have is another panel, a panel of buttons, a typical one. Here again, you have the display, which says the current position of the lift. It indicates whether the lift is moving up or the lift is moving down. And here you have a set of buttons, which indicates which floor you want to go to, right? You all know this very well, no point repeating it. Then additionally, on the bottom, you have one emergency button. Forget the emergency button for this particular application. Let's assume we don't have any emergencies. And there's another, this one, two buttons, one for door opening and another one for door closing. Here, we are not using the door closing button. We're just assuming what happens is whenever the lift comes to a particular floor, stops at a particular floor, the door automatically opens. That's a normal process. And it remains open for a predefined amount of time. Then it automatically closes. But then if you want to, if you want to open it further, what you could do is press this door open button. Then it again opens and remains open for a certain amount of time, after which it again tends to close down. So that is this door open button. We'll be using the door open button. Pressing that would open the door for a predefined amount of time, after which it automatically closes. You also know that a lift door can only open when the lift is stationary at a particular floor. This is a safety requirement. You cannot open a lift door when it's moving. It can be opened only when it happens to be stationary at any floor. That is for the safety of people inside. Rather, there's a second requirement. This can be only open when there's actually two doors. One door is on the lift. There's another door on each floor. That is important because if that door was not there, someone would fall into this particular chamber in which the lift moves. So normally what happens is the lift door opens when first the outer door opens and then the lift door opens. But anyway, let's just assume that the lift door can open, normally opens when it is at a particular floor, when it is stationary. It remains open for a certain amount of time, then closes. And if you want to open it further, you can press this open door button again. And that will open the door for a predefined amount of time. Okay, so this is well known. This outside on each floor, what you have is well known, nothing new here. Now, just let's try to put what we already know into some point-wise logic. Now, from this point, I'll require your participation. When does the lift move up? Okay, for the time being, let's break up the problem into two parts. Because if you try to do the whole logic, as I said, this is probably the most complicated of all programs that you've developed so far in terms of logic. So let's not try to do it at one go because it will make it far more complicated. Let's break it up into two parts. First, let us assume that the lift is controlled only by the external buttons on each floor. That means these buttons. On each floor, you have these buttons. You want to go up or you want to go down. Let's forget the panel inside the lift. Let's forget this. So let's just consider the behavior of the lift or the logic which would guide the movement of the lift, which will determine the movement of the lift based on these two buttons, which is located, as you know, on every floor. So for the time being, forget the buttons that is located inside the lift on that particular panel. So when does a lift move up? As you can guess, the lift moves up when it is called up from any floor over the present location of the lift. Lift এখন যেখানে আছে তার উপরে যে কোনো ফ্লোর থেকে যদি লিফটকে ডাকা হয় তাহলে লিফটে উপরে যাবে। So the lift goes up whenever it is called from any floor above the present position of the lift. And similarly, when does the lift go down? When it is called from any floor that is below the present location of the lift. এখন লিফটে যেখানে আছে তার নিচে যে কোনো ফ্লোর থেকে যদি লিফটটাকে ডাকা হয় ডাকা হয় মানে এই দুটো পুশ বাটনের মধ্যে কোনো একটা যদি প্রেস করা হয় তাহলে the lift moves down. Okay, so this is the first thing. When does the lift move up? When does the lift move down? And what is very obvious? When does the lift stop? There are many conditions when the lift stops. The first very obvious condition is when it is not being called from any floor. If there's no people in any of the floors, if no one wants the lift, obviously the lift doesn't move. The first one is very obvious. The lift stops if it's not called from any floor. You are not pressing this up or down buttons on any floor. That is very obvious. But probably the second point is not that obvious. When the lift is moving up, it could move up, it could remain stationary, it could move down. That are the three possibilities, right? So when a lift is moving up, when does the lift stop? The lift is moving up, it stops if one, if it reaches the topmost floor, then obviously the lift has to stop. It cannot move any further upwards. Or
it reaches the topmost floor.
Sorry?
Sir, it reaches the topmost floor, or when it is at the ground floor, it is moving down and it reaches the ground floor.
Yeah, that are the two most obvious parts. So first, let's consider
someone
the up part
with
first.
respect.
We'll come to the down part later, right? So up is okay. As you just said, what is very obvious, when it reaches the topmost floor, it stops. But it does not always move to the topmost floor. So the logic is, when it reaches the topmost floor, it stops. Definitely, it has to stop. Or while moving up, if it reaches the topmost floor from which it was called. Say the lift now is at the ground floor. Someone at floor 1 press the button. Someone at floor 2 press the button. Someone at floor 3 press the button. Right? So here the lift would sound from ground floor, comes to floor 1, comes to floor 2, comes to floor 3, but does not go to floor 4 because no one has pressed a button on floor 4. So it stops while going up, it stops when it reaches the topmost floor, that is obvious. But it also stops if it reaches the highest floor from which it was called while moving up. While it was moving up, the highest floor from which it was called, it goes there and stops. As I said, say the lift was at ground floor, someone presses a button on floor 1, someone presses a button at floor 2, no buttons are pressed at floor 3 and floor number 4. So the lift will start from ground floor, it will go to floor 1, it will go to floor 2, but it will not move any further upwards. For the time being, let's forget the panel inside the lift. Okay, that's another way where you decide where the lift is going to go. Let's forget that part. I'm just breaking up the problems into two halves to make it simpler. So just if you concentrate on this outer buttons that is located on each floor, then the lift stops while moving upwards when it has reached the highest floor from which it was called or from which its presence was requested, whatever you say. So this is one important requirement, or I mean, this is just the logic, which is very obvious. We know all this, we know this very well, but just we're putting this in words. We're trying to arrange it in something in a meaningful way. So when it goes to the topmost floor, it obviously has to stop. But when it's moving up, it also stops if it has reached the highest floor from which it has received a request, and that is it. Now, point 2. The lift is moving up. Say it's at ground floor, right? Let's take specific examples. It's the ground floor. Someone who's at floor 1, he wants to move down. He presses the down arrow. And someone who is at floor 2, he wants to move up or he wants to move down, whatever. He presses either the up arrow or the down arrow. So he also presses the down arrow. So person at floor 1 wants to move down, presses the down arrow. Person at floor 2, he also wants to go to the ground floor. He also presses the down arrow. There's no one on floor 3, no one on floor number 4. So the lift starts off at the ground floor. A button has been pressed on floor 1. That is the button which says that I want to go down. A second button has been placed on floor 2. The lift has also been called from floor 2. That again says that I want to go down. So what does the lift do? Starts moving up because it has been called from 2 upper floors. But when it reaches floor 1, does it stop? It has been called from floor 1. But what has been said that the person on floor 1 wants to go down. He doesn't want to go up. So what is your normal experience say? When the lift comes to floor 1, should the lift stop or doesn't it stop? What should be the requirement?
It should not stop.
Yeah, because he is wanting to go down. He's not interested in going up. So what's the point in stopping there? He doesn't need to pick up the person now while he's going up. So the lift, though someone has pressed a button on floor 1, since that person wants to go down, the lift does not stop at floor 1. It goes to floor 2. Even that person wants to go down, but it happens to be the highest floor from which the lift has been called. So it stops at floor 2. Remember, even the person at floor 2 say he wants to go down. He wants to go to the ground floor. But that happens to be the highest floor from which the lift has been called. So there, in spite of the fact that the person wants to go down, the lift stops at floor 2. You can understand that logically that the lift has to collect this particular person, has to take in this particular person at floor 2. Then he starts coming down, stops at floor 1 because that person wants to go down, then goes to ground level. So that's the reason why we have this particular point 2. While the lift is moving up, the lift stops if it reaches a floor where the up button has been pressed. Floor number 1, you have pressed a button. It has been called from floor number 1, but the person on floor number 1 wants to go down. He has not pressed the up button. He has pressed the down button, indicating that he wants to move down. So when the lift is moving up, when it reaches floor number 1, it does not stop because on floor number 1, okay, someone has called the lift from floor number 1, but not to go up, to go down. So it stops only if it reaches the top of the building. Obviously, it has to stop. Or it reaches the highest floor from which it has been called. There it stops. And it does stop if it reaches an intermediate floor from where an up button was pressed. Multiple floors, buttons were pressed. So while it is moving up, at some intermediate floor, floor number 1, floor number 2, if someone has pressed the up button, the lift would stop, pick him up, and then move upwards so that he can be dropped at whatever floor he wants to get down to. So that is the logic behind when the lift stops, when it is moving up. You have an identical logic as to when the lift would stop when it is moving down. So I think this summarizes the state of the switch down in a flow chart. If that is convenient, you could put it in a state transition diagram. If that is convenient, you can write it in text. Because the most important part is first to define what the logic is in this particular application. So remember, this logic is just based on lift movements based on the switches on each floor. We have not included the switches inside the lift by which you say that I want to go to this particular floor. That's still not been included. So when does the lift, this one stop while moving down? When it's come to the ground floor, it cannot go any lower than that. Of course, I'm assuming that there's nothing below ground here. Or while it's moving down, it stops when it reaches the lowermost floor or the lowest floor from where it has been called. And secondly, when it is moving down, it stops at an intermediate floor, provided the down button was pressed at that particular floor. If you press a button at a particular floor, it's not guaranteed that the lift is going to stop. It's only going to stop if it's moving down and you also want to move down. So if it stops at an intermediate floor, provided the down button was pressed at that particular floor. So this is very similar to what happens when the lift stops when it's moving up. So this summarizes when the lift stops while it's moving, both in the upward direction and both in the lower direction. And finally, coming to what happens when you press any button inside the lift, this is straightforward. Whatever button you press, whatever floor number you press, the lift is going to stop at that particular floor. There's no conditions here. It's straight. You press floor number 3, the lift stops at 3. You press this one ground, the lift stops at the ground floor. So here the logic is very straightforward that whatever button you press, whatever floor you indicate, the lift stops at that particular floor. Remember, all these buttons are essentially push buttons. Okay, they are not latched buttons, because then you have a serious problem if you use latch buttons here or even other floors. They're all push buttons, so all states must be latched if you want that particular state to be retained. And finally, coming to the door logic, we are not considering the outer door. We're just considering the door inside the lift. That you know that a door opens only when the lift is stationary. If the lift is moving, a door cannot be opened, irrespective of whether you press that open door button or not. When it reaches a particular floor and stops at that particular floor, that's important, not merely reaches the floor. Whenever it stops at a particular floor, the door opens automatically, remains open for a certain amount of time. You implement that using a timer. After that, it automatically closes. But then if that time wasn't sufficient, then you can press that open door button. It then extends that door open duration for a certain amount of time, then closes. You can again press the door open button. Again, it would extend the door open duration. So that process continues. So that is how the door behaves. The interlock is door can only be opened only when the lift is stationary at a particular floor. Okay, fine. Now, to make your problem a little more difficult, further difficult, think is okay. One is you've got to develop the logic, the controller, which controls the movement of the lift. So what should be the output of your controller? What are the inputs of your controller, and what are the outputs of your controller? The article that I've included, there's a small write-up that I've included. You'll find that well described in very less words, okay? But I think you can guess what are the inputs that you need and what are the outputs that you need. Outputs are just from the controller is simply 2 outputs. One which says the lift goes up and one which says the lift goes down. This is made, as you know that it has okay, you've got a room-like structure. It is guided by rails on the side. I'm not sure if you noted that. I mean, so that it can just move freely in a vertical direction. It cannot move in a horizontal direction, right? That's very important. So it's got guides on both sides, which ensure that the lift can move freely vertically, but not in a horizontal direction. And if you must have observed, possibly the department, that there's a rope which ties the lift, goes straight up. On the top, you've got a pulley which is driven by a motor, which is responsible for the lift moving up or down. And the other side of the rope again comes down and it's got a counterweight, right? So normally the weight is selected so that it is equal to the weight of the empty lift plus around 50% of its capacity. I mean, if it can take 10 persons, take the approximate weight of 5 persons. So the counterweight is the weight of the empty lift plus whatever is the weight of 5%. Why do you have a counterweight? You find that explanation very well, but probably you can guess. Because if you use a counterweight, then the amount of torque that is required on the motor, because if the two weights perfectly balance each other, I mean, if the weight of the lift is just identical to the weight of the counterweight, then the torque required to move the structure is 0. The only torque that is required is the torque necessary to overcome the friction in this particular system, because the two weights perfectly balance each other. If the counterweight did not exist, then the torque that would be required from the motor would be very large. It would have to pick up the entire load, the entire weight of the lift. But here the weight of the lift is balanced by the counterweight. Balanced or closely balanced is not always perfectly balanced. from the motor is very small. But anyway, the motor has two inputs, one which says rotate clockwise, for that the lift moves in one direction. Another input says rotate anti-clockwise, for which the lift moves in a second direction. And if both these inputs are off, then the lift is stationary. So the output of the controller means the controller is a device which controls the motion of the lift depending upon the inputs. The output of the controller is this one, two signals saying the motor should rotate clockwise, the motor should rotate anti-clockwise, or the motor simply should not rotate. So that is simply the output of the motor. The input of the motor, there are various inputs. Each switch that is connected on the floors is a switch, is an input to this particular controller. The panel, all the switches connected inside the lift, that are inputs to the controller. Plus, what you can guess is the lift needs to know its present location, because a lift always has to stop exactly at the position of a floor. If you say, I want to go to floor 2, as you must have observed, the lift always stops perfectly aligned with the floor of floor 2. It does not stop upwards, it does not stop below the level of the floor of floor 2. So there must be some mechanism, there must be a sensor which tells the lift its exact position. This is very important, so that lift can stop exactly at the desired position. Actually, there are two sets of sensors. One set of sensors gives the actual position of the lift. It's not very accurate, but it gives the position of the lift. And the second sensor is triggered whenever the lift reaches a particular floor. So for every floor, you have a sensor which accurately defines that the lift has reached that particular floor position. Now it is safe to open the door if the lift has to stop at that particular floor. So you have one sensor at each floor which says that the lift has accurately reached that particular floor position. That is the basis on which the door is opened, if the door has to be opened. And second, it also has a sensor which gives an approximate position of the lift. Forget, low-cost lifts like we have in a department. If you go to some high-rise building, which have better lifts, you'll find that the lift initially starts off at a slow pace, accelerates, starts moving fast. You cannot move slow in a high-rise building. It will take a huge amount of time. And when it's about to stop, before stopping, it decelerates. It slows down and finally stops at that particular floor. That is very important to ensure a smooth journey, because if the lift were to moving at a high velocity, comes to a particular floor and suddenly brakes, you know what happens if you're moving in a vehicle and the vehicle suddenly brakes. That's not the best of experiences that you get. So that is also implemented in the lift. The lift decelerates as it approaches a particular floor, comes to a stop. Again, when it's moving up, it gradually accelerates and then gets up to the maximum speed. So when to decelerate, when to accelerate, that is decided based on the position of the lift. So you need to know the position of the lift. You need to know that you are approaching a particular floor, so that you have to decelerate. And finally, when you exactly reach that particular floor, a separate sensor gives you that particular signal. And so then you open the door, you stop and open the door. I mean, these sensors in the simplest of cases is a limit switch. There's a limit switch at each floor. So when the lift reaches that particular floor, it strikes that particular limit switch and you get an output. It could be proximity sensors, it could be various other sensors, but vast majority of the cases, you have a limit switch at every floor, which gives you a signal that the lift is at that particular floor. And approximate position, again, it could be an encoder. Incremental encoders is one popular solution. There are various other types of sensors that you can use to gather an approximate information regarding the position of the lift, which is important for acceleration, deceleration, and all those additional purposes. Okay, now coming back to the problem, in our case, we do not have a physical lift. And even if we had a physical lift, no one will allow you to test your controller directly on an actual lift, because you understand, if you make a error in your software, if your software, if your program has bugs and you connect that directly to a physical lift, you can imagine what could possibly happen if your software doesn't work the right way. No one is going to take that particular risk. So first, you have got to try out a software, you've got to try out a program on a simulated model of this one lift. I know you don't like that, but that is the standard practice. No one is going to try out your initial software, initial program on a physical lift. It's not worth that particular risk. So You got to have a very crude model of the lift and then try out your logic on that particular lift. Now, how do you develop a model? I'll just give you a demo of that. This is the best I could manage. This is just a model. There's no controller here. So this one, I didn't have enough space to put all the four in the same line. This one is what you see in the upper floor. You just can go down. This is on the floor number 3. You can go up and go down. And this is floor number 2. This is the ground floor. You can only go up. Okay, so if I run this, I repeat, the whole thing is a simulation. I just come to how you need to. So it's still at floor 1. It's gone to floor 2, and finally of this. Now, if you want to move down, again the same simulation working. So floor 3, floor 2, floor 1, and until you get to the ground floor. Now, this is the model of the lift. This is what you need to first develop before actually you can test out a controller. Because if you just test a controller, you need to check that out, right? You can't do that manually because in this case, the number of inputs and outputs are pretty large. So doing that manually would be quite difficult. So you need this particular model. Now, how do you develop this particular model? The lift could be any object. This one is just a picture that has been copied from the net. You could take any, even you could take a square box, which is supposed to represent this one, the lift. The lift moving up and down, how do you animate that? In courses, you this one right click on any object, you go to its properties. On the properties, you'll have something called absolute motion. That's a part of the properties of any object. In absolute motion, you can define x, that is x coordinate, and the y coordinate of that particular object. Here, the lift is moving only in the vertical direction. So what is changing is the y coordinate. It's not moving in a horizontal direction. So x coordinate of this particular object is not changing. Only the y coordinate is changing. So assign a variable with the y coordinate of this particular object. Go to absolute position, and there with the y coordinate, associate this particular variable. So as that particular variable changes, so the position of the lift changes. Here I've used 3 pixels because it's directly based on the number of pixels. It will depend upon the size of your screen and the resolution of the screen. But in this case, I have this one changing the position by 300. So this position is 0 and the topmost position is 300. Accordingly, the position of the lift is changing. Now, so lift is moving up. What that means is the position of the lift is starting from 0 when it's at the ground floor, increasing to a maximum of 300. Now, how does this position of the lift increase? How do you do that in a program? Again, you can do it in 2 standard ways. One is you can have an up-down counter fed by a clock. So if you feed the up count line by a counter, that's continuously counting up. So you count up to 300. And the count value is associated with this particular lift position. So as the count value increases, the position of the lift, this one changes, and you see on this particular animation or on this particular visualization, you see as if the lift is moving up, right? Now let us associate that, let's consider that 0 to 300 is the range over which this particular lift is moving. So 0 could be ground floor. When the count value is 100, it is at the first floor. When the count value is 200, it is at the second floor. When the count value is 300, it is at the third floor. So that way, you can simulate the output of the floor switches. A little while ago, I said that each floor has a sensor, which is predominantly or primarily a limit switch, which says that the lift presently is at that particular floor. Now, I don't have a physical lift, I don't have physical sensors, but I need to simulate the output of these sensors. If you have 4 floors, so you need 4 sensors. One saying that lift is at ground floor, the second one saying that lift is at floor 1, floor 2, and floor 3. So what you simply need to do in your program is compare the present lift position with 0. If the output is 2, it is at ground floor. Compare the present lift position with 100. So that's to floor 1. Compare with 200, floor 2. Compare with 300, floor 3. That's assuming that you have 4 floors, and that's assuming that the lift position changes from 0 to 300 as the lift moves from the bottom to the top. I mean, that depends upon what you do. So that's just an idea of how you could physically simulate the position of the lift from a minimum to a maximum and generate the flow, sensor outputs, which flow the lift is presently in, because these sensor outputs become the input to your controller. So that is one. And second is, you also, this particular flow position has been displayed as you see, flow 0, flow 1, flow 2, flow 3. So depending upon the output of the flow sensors, you also need to generate this particular display. If it's at the ground floor, you display 0. If it's at the first floor, you display 1, second floor, display 2, and so on. So that is also used to generate the flow display that is provided on each floor and also provided inside the lift. Inside the lift also, you have a display of the current flow position. So this program with the so-called model of the lift, one would generate a position of the lift. So if the lift input to this model is lift moves up, lift moves down, or something like this. It's just a suggestion, not that it's got to be this. One input is lift is moving up, second input is lift is moving down. If both the inputs are false, so lift is neither moving up nor moving down, so the lift is stationary. What is the output lift position? This position range, of course, depends upon the size of your screen. So in my case, it is 0 to 300. So if lift up and lift down both is 0, the lift position remains fixed. That means this one, you're not providing anything to your up counter line. You're not providing anything to down counter line. So the count value remains fixed, and that becomes the position of this particular lift. Now, if the lift up is true, then this particular counter up counts. If the lift down position is true, this counter down counts. That's one way of doing it. The second way, instead of doing it using an this one up counter and down counter, you can do it using an integral function, which you used in the previous example, or probably will use in the previous example, to simulate water level inside a tank. It's exactly the same thing, a replica of the same thing. There, again, the level was increasing or decreasing. Here, instead of level, what is changing is the position of the lift, again, starting from the minimum value up to a maximum value. What are the further outputs of this particular model? The further outputs is the output of the 4 position sensors, whether the lift is presently at ground floor, first floor, second floor, third floor. That is an important input to your controller. And plus, lift at floor, that's a number which says what is displayed. I mean, whether you have 0, if it's at ground floor, you have 1, it's displayed at this one, floor 1, and so on. So that's a number which is ultimately displayed at each floor and is also displayed inside this particular lift. So the difference between these two outputs, one is the output of each sensor. That's a Boolean variable. So if it's at ground floor, the corresponding output is true and all other outputs is false. Obviously, a particular lift can be only at a particular floor at any point of time. So of the 4 outputs, only one output would be true and the other 3 would be false. So here you have an output of 4 Boolean variables representing 4 floors. One is which represents the current position of the lift. That is, when the lift is at ground floor, it's 0. It remains 0 until it reaches floor 1. So for all positions of the lift from ground floor below first floor, it is 0. From first floor to just below second floor, it's 1. Second floor to any position just below third, it's 2. And finally, it's 3. So that is an output that is generated, a number that is generated, which is displayed on every floor, and which is also displayed inside the lift. So this is a model of the lift. This also provides a particular visual display. And the outputs of this go to your controller, and the output of the controller, which says the lift is moving up or lift is moving down or lift is not moving, becomes the input to this particular model. In addition, controller also has additional inputs. All the flow buttons or all the buttons inside the lift, those are also inputs to your controller. For example, in this particular case, for 4 floors, you have 1 button, 2, 3, 4, 5, 6. All the 6 buttons that are located on the 4 floors are inputs to your controller. Plus, inside the lift, you'll have 4 buttons, ground, 1, 2, 3. So effectively, you have 10 buttons, 6 on the floors and 4 inside the lift which become inputs to your controller. Plus, you have an additional button for opening the door. So, as far as inputs are concerned, to your program, to your controller, you have 6 push buttons on the floors, 4 push buttons, assuming this one 4 floors, 4 push buttons inside the lift, plus the present lift position, whether it's in ground floor or first floor or second floor or third floor, 4 position sensor outputs generated by a model, which again becomes inputs to your controller. So 6 push buttons, 4 buttons inside, and 4 flow sensors, which gives you whether the lift is tells you whether the lift is present at that particular floor. So that gets to 14. You can assume that you need a model. So physically, simulating or applying 14 inputs manually would be a difficult proposition. So I hope I've been able to just describe the problem. I have not tried to describe a solution. No intentions of doing that, because it could be worked out in multiple ways. So no point in forcing the solution on you. I just was trying to discuss the problem. Anyway, you all were aware of the problem, probably just being stated in a point-wise fashion. So this is our last assignment. Of course, in the HMI part, you'll have your model simulation, which will actually show the lift moving and up and down. Plus, additionally, you have panel here, which is a 4 button inside the lift. Plus, you can show a button whether the door is open or closed. That is it. In addition to this, you'll have a panel inside the this one lift, ground 1, 2, 3. Another push button for opening the door. That is it. That will probably form your HMI. And you so probably that is what I was trying to discuss. I don't think I'll be giving a write-up on this, because the problem is very well defined. I mean, by experience, you know it all. What needs to be done. The only thing is, how does it, how do you do it? That is what you need to address. মোটামুটি আমার বক্তব্য শেষ।
তোমরা কিছু ডেমো দিতে চাও?
শুনতে পারলাম না। যারা ডেমো দিতে চাও, অন্যরা ওই তোমার জাস্ট নামটা লিখে চলে যেতে পারো।
প্রেজেন্ট করবে?
হ্যাঁ। তোমার রোল নম্বর কত?
27। এটা ইনিশিয়ালি সেটআপ মোডে আছে এখন। 0.5 ইনক্রিজ করছে, এটা 0.5 ডিক্রিজ করছে, মিনিমাম 0-তে যাচ্ছে। ম্যাক্সিমাম 3-তে যাচ্ছে, আর ডিসপেন্স করলাম। এখন কোনো বাটনই কাজ করবে না বাকি। কোনো বাটনই কাজ করছে না, হোল্ডটা শুধু কাজ করবে। তারপরে এ দুটো কাজ করবে না, ডিসপেন্সও কাজ করবে না।